Hi there, this is Quantum Phenomena. This is lesson 2, part of the A-level physics scheme of work. So let's have a look. So a bit of information first, the vacuum photocell. So the photocell is an application of the photoelectric effect. Looks something like this. So light is incident on a metal plate, and we call it the photocathode. If the light's frequency is above the metal's threshold frequency, electrons will be emitted. The electrons passing across the vacuum from the photocathode to the anode constitute an electric current, which can be measured with a microammeter. Remember, if the incident light is not of the threshold frequency, if it's below, then no electrons will be emitted. And it doesn't matter how much light you shine on the photocathode, nothing would happen. Okay, it has to be the threshold frequency. Because remember from last lesson, only one individual photon can interact with one electron. So, bit of maths, how do we obtain Planck's constant? So we have a graph like this, and it's from the gradient. You could be asked to show this or calculate this in an exam. So the equation is HF equals the work function plus the kinetic energy. And as you can see, we've got kinetic energy on the y-axis and frequency on the x-axis. So if we arrange to get kinetic energy is equal to HF, the photon energy, subtract the work function. So kinetic energy is on the y-axis, the frequency is on the x-axis, so the gradient of the graph would give Planck's constant. So this is correct. Just out of interest, the plus c-intercept gives you the work function, which would be down here. Okay, let's move on. Hopefully that's okay. If you want to rewind at any point or pause, remember, please do. Quick question then. If you want to pause and have a go. The graph shows how the maximum kinetic energy, EK, of photoelectrons emitted from a metal surface varies with the reciprocal of the wavelength of the incident radiation. And this question is asking you to find out what is the gradient of the graph. So it's similar to the last one, however, this time we've got wavelength instead of frequency. So there's another, the original equation is HF equals the work function plus the kinetic energy. But remember, we've got the equation C equals F lambda. And frequency would be C over lambda. So we can substitute that in instead. We've used this equation many times before. So hc over lambda is equal to the work function plus the kinetic energy. So we need to rearrange to get y as kinetic energy. So kinetic energy is equal to hc over lambda minus the work function. So the kinetic energy is on the y-axis. The x-axis is 1 over lambda. So that's kind of this. So that'll be x. So the coefficient of x is the gradient. That would be hc. So the gradient m is equal to h, Planck's constant, times c. So that's the gradient of the graph. And if you wanted to find the Planck's constant, h, you would just do the gradient divided by the speed of light. Hopefully that's okay. Let's move on to the next bit. The electron-volt. This is important, the electron-volt. And by definition, it is the amount of energy gained by an electron when it passes through a potential difference of 1 volt. So there's an equation from electricity, which goes back to GCSE. Energy gained is equal to charge times the change in potential, or E equals QV. So the energy gained, so the charge of an electron is 1.6 times 10 to the minus 19 coulombs, multiplied by a voltage of 1 volt. So that gives an energy gained of 1.6 times 10 to the minus 19 joules. And we call that 1 electron volt. So 1 electron volt is 1.6 times 10 to the minus 19 joules. And what you can be asked to do is it can give you an energy in electron volts, and you have to do conversions. So let's have a look at one as an example. Let's say that we had 3.2 electron volts, 3.2 eV, electron volts, and we needed to convert that quantity into joules. All we do is multiply by the charge of an electron, 1.6 times 10 to the minus 19, or the energy, sorry, for 1 electron volt, and we get a total energy in joules of 5.12 times 10 to the minus 19 joules of energy. So that's very useful to know. You will probably have to utilise that in an examination. And then we can go backwards. So if we wanted to go from 5.12 times 10 to the minus 19 joules back to electron volts, we just divide by 1.6 times 10 to the minus 19, which would take us back to the 3.2 electron volts that we started with. So, quick question, recap from last lesson. If you want to pause and have a go. Calculate the energy in electron volts of a photon of ultraviolet light of frequency 8 times 10 to the 14 hertz. Planck's constant's given for this one. So let's find the energy in joules. So E equals HF. So we've got 6.63 times 10 to the power minus 34, multiplied by the frequency 8 times 10 to the 14 hertz. And that gives an energy of 5.3 times 10 to the minus 19 joules. And the question wants us to convert that into electron volts. So we need to divide by the 1.6 times 10 to the minus 19. And that gives us an answer of 3.3 electron volts. Hopefully you got that right. Let's move on to the next one. So here's a question. If you want to pause and have a go. Photons of wavelength 290 nanometers are incident on a metal plate. The work function of the metal is 4.1 electron volts. What is the maximum kinetic energy of the emitted electrons? So we've got the work function equation. So we've got HF equals work function plus kinetic energy. But we haven't got frequency, we've got wavelength. So we're going to use a different form. So it's the hc over lambda again, equals work function plus kinetic energy. So let's do hc over lambda. So h is 6.63 times 10 to the minus 34, multiplied by the speed of light, 3 times 10 to the 8, divided by the wavelength of 290 times 10 to the minus 9. And then what we need to do is subtract the work function to give us the kinetic energy. So we're going to subtract the work function. Just below here, I'm going to convert the 4.1 eV into joules. So it's 4.1 electron volts multiplied by 1.6 times 10 to the minus 19. So that gives the work function in joules of 6.56 times 10 to the minus 19 joules. Then we just need to do the h over lambda from earlier and subtract the work function, the 6.56 times 10 to the minus 19. And that will leave us with the kinetic energy. So in your calculator, that'll give you a kinetic energy of 2.99 times 10 to the minus 20 joules. Another common exam question would be to extend this question, which we can actually do now. Hopefully you got that right. I'm going to remove this and then extend the question. So the question might ask for the maximum speed of the emitted photoelectron. Speed of photoelectron. So if you want to have a go at that, please pause and have a go. And then I'll take you through the answer. So we've got the kinetic energy of the photoelectron, which we just calculated, to be 2.99 times 10 to the minus 20 joules. And what we can do with that is use the kinetic energy equation. So the kinetic energy equation is a half mv squared. So to get speed v, we need to multiply by 2 and then divide by m, and then square root. So 2 times the kinetic energy, divide through by m, and then square root to get the speed. So we've got 2 lots of 2.99 times 10 to the minus 20 divided by the mass of an electron. So you should know this by now. Maybe you had to look it up, but that's okay. But it's 9.11 times 10 to the minus 31 kilograms. And then square root our answer. And that gives a speed of 2.6 times 10 to the 5 meters per second. If you got that, well done. Let's move on to the next one. Ionization, some notes. So an ion is a charged atom. Normally atoms are neutral. Well, they are neutral. If they have a charge, be it a positive or a negative electrical charge, then they must be an ion. They're no longer an atom. Ions are created by adding or removing electrons. So in that situation, an incoming electron has collided with another electron and knocked it out of the atom. So the diagram shows the creation of a positive ion from the collision of an incoming electron. And ionization can be caused by nuclear radiation, such as alpha, beta and gamma, heat, or passing an electric current through a gas, such as a fluorescent tube, which we'll look at in a different lesson in more detail. So let's see what's next. Ionization energy. So this is pretty straightforward. Ionization energy is the energy required to remove an electron from an atom. And ionization energy is often expressed in electron volts. Excitation then. So here's a diagram that you could see in an exam, and it's the energy levels of an atom. So excitation is the promotion of electrons from lower to higher energy levels within an atom. Some of the incoming electron's kinetic energy has been used to move the electron to a higher energy level. The electron is now said to be in an excited state. So that's from the diagram earlier, where the external electron came into the atom and interacted with a orbiting electron. So that's what excitation is. So let's look at the next bit. So electron energy levels in atoms. Electrons are bound to the nucleus of an atom by the electromagnetic attraction. A particular electron will occupy the nearest possible position to the nucleus. And this energy level, or shell, if you do chemistry, is called the ground state. It's also the lowest possible energy level for a particular electron within an atom. Only 2 electrons can exist in the lowest possible energy level at the same time, and further electrons would have to occupy higher energy levels. So you should know that from GCSE chemistry. Remember to pause at any time to make any notes. So energy levels in atoms. Energy levels are measured with respect to the ionization energy level, which is assigned to 0 eV. All other energy levels are therefore negative. So the ground state in the diagram opposite is minus 13.6 eV. Energy levels above the ground state, but below the ionization level, are called excited states. Different types of atoms have different energy levels. So what happens is an external electron, which we talked about a moment ago, could come into an atom's region of space and interact with an electron, give it energy and excite it into a different energy level. So an electron could come from the ground state and go up there, or it could go to the next one, the next level, or it could go to the top, or it could receive enough energy to leave the atom completely. What we're interested in particularly is what happens when the electron comes back down. So let's say there's an electron residing in this level, the second level. That electron could come down to this level, or it could come down to that level, or it could go down to the level 1, and then come down again. Each time there's a transition in energy, a photon is released, and the photon energy is equivalent to the difference between the designated energy level energies. So we'll do a calculation on this shortly with an example question. So remember, so when it drops an energy level, so a photon will be given off. This second transition, another photon will be given off of this energy, the difference in energies. And in this state, between these two energy levels, there would also be a photon given off. And the energy will be the difference between these two energies. So let's look at some more notes. De-excitation, so that's what I've just been talking about. Excited states are usually very unstable. So within about 10 to the power minus 6 seconds, the electron will fall back into a lower energy level. And like I said, it emits a photon as it does so. So with each fall in energy level, a photon of electromagnetic radiation is emitted. So the emitted photon energy is just the difference between the energies. And I'll let you have a go at the next question. So here it is. If you want to have a go and just try and think about this and see if you can figure it out, that'd be great. You could use it as an example question. The next lesson is going to be, lesson 3 in the quantum series, is going to be a couple of these questions, but big versions of those questions. So it'll still take maybe 10 minutes. So you can have a go at this, but I'm going to show you the answer, or you can just let me use it as an example question and then move on to the next video. So if you want to have a go, please pause. So it's the energy level question. Calculate the frequencies of the photons emitted when an electron falls to the ground state at 10.4 eV, from excited states 5.4 eV, and B from 1.8 eV. So there's two questions here. And for each one, we just need to do the change in energy. That will be the energy of our photon that's being emitted, and then subsequently calculate the frequency. So the first one, we're going to start at 10.4 electron volts. And we're going to move to the 5.4 electron volts. So we need to do the difference in energies. So it's 10.4 minus 5.4, which gives us 5 electron volts. And what we need to do is turn that into joules. So to do that, we need to do 5 electron volts multiplied by 1.6 times 10 to the minus 19 joules. And that gives us a change in energy of 8 times 10 to the minus 19 joules. So that would be the energy of the emitted photon. Then what we need to do is find the frequency. So we're going to use the equation E equals HF. So the frequency would simply be the energy divided by Planck's constant. So the energy is 8 times 10 to the minus 19 joules divided by Planck's constant, 6.63, times 10 to the minus 34 joule seconds. And that gives us a frequency of the photon of 1.2 times 10 to the power of 15 hertz. So that's the first one done. Let's do the next one. Hopefully that went okay. So the next one, we go from the 10.4 eV to the 1.8. So we need to do 10.4 eV minus 1.8 electron volts. And that gives us a change in energy of 8.6 electron volts. Then we need to turn that into joules. So we need to do 8.6 eV multiplied by 1.6 times 10 to the minus 19, which gives us an energy, or change in energy, which will be the energy of the photon, of 1.376 times 10 to the minus 18 joules. Then we just need to find the frequency. So the frequency, so we're going to use E equals HF. So the frequency will be the energy divided by Planck's constant. So the energy is what we just calculated, the 1.376 times 10 to the minus 18, divided by Planck's constant, 6.63 times 10 to the minus 34 joule seconds. And that gives us a frequency, a final answer, of 2.1. times 10 to the power of 15 hertz. Hopefully that went okay. So a bit of a long lesson, but hopefully worthwhile. Thanks for watching, and I'll speak to you soon.